In this video, we're going to do a quick overview of stereoisomers. As we know already, there are isomers that exist. There's many types of isomers. You can have constitutional isomers, which is the topic of our previous videos. You can also have stereoisomers, which is what we're going to focus on in this video here. Stereoisomers can be diastereomers or enantiomers. We'll focus on diastereomers first. So stereoisomers are called spatial isomers. They have the same molecular formula as each other, and their atoms actually have the same bonding sequence, so same order of bonding, but they actually differ in their 3D orientations in space. And so there's a few ways you can differ in your 3D orientation. You can differ as a diastereomer, or you can differ as an enantiomer. And so right now we're going to focus on the diastereomer component. Diastereomers are also called geometric isomers. So we sometimes call those cis-trans isomers as well. It's all the same thing. The tricky part here is that you just have to become familiar with terminology. So we have stereoisomers, which can be diastereomers or enantiomers. Diastereomers are called geometric isomers, and they can be called cis-trans. So diastereomers are stereoisomers that have the same molecular formula. They have the same bonding sequence, but the arrangement about the double bond is different. The way we arrange the components groups near the double bond is a little bit different in the two different isomers. And so we'll take a look at how they're different. So why is it important to have a double bond? Well, you can't really have diastereomers if you don't have a double bond. And that's because you need to prevent rotation to have two distinct molecules. So let's take a look at the examples over here. Here we have two diastereomers. We have cis-butene and trans-butene. Notice that they have the same molecular formula, 1, 2, 3, 4 carbons. So C4H8. And over here, C4H8. Everything's bonded in the same sequence. A C here, 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 and here. A C here, 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 and here. Same order, relative order. The double bond is in the same position. But what's different is the way the groups are arranged about the double bond. In cis-butene, the two CH3 groups connected to double bonded carbons are both on the same side. They're above. Okay. Whereas in trans-butene, the CH3 groups attached to the carbon-carbon double bonds they're on opposite sides. One is above, one is below. And the reason that this can happen when you have a double bond is because a double bond is strong and cannot rotate, whereas a single bond can rotate. So here we have a single bond, and so this rotates. So that's why this and this are actually the same, because this will basically become that as a single bond rotates. So they're not different molecules, they're the same thing. But when you have a double bond, these are actually distinct molecules, because this can never become this over here because there's no rotation that happens. So these are actually two distinct molecules that are formed in their own respective ways. So to have diastereomers or geometric isomers, you need to have a double bond. You cannot have single bonds. So basically, when you see double bonds, those molecules, they have constitutional isomers, but now they have the additional variety of diastereomers because you have that prevention of that rotation that happens. Now, on that double bonded carbon, you need to have two different groups. So for example, here you have a CH3 and an H. That's two different groups. It could have been a Cl instead, doesn't really matter. Here on this carbon, a CH3 and an H. So two different groups on each one, because you want to be able to have different combinations. Like if I had two of the same groups, so let's say here I had CH3H, and here I had CH3CH3, here's two of the same groups. So if I flip that, it's still the same molecule because it's still CH3 here and CH3 there. Whereas here, because I have two different groups, when I flip one of these or the other, now I have a different combination, H and CH3 here, CH3 and H here, whereas over here it's CH3, 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 H. It doesn't matter what I do. When I flip this, it's always the same combination of stuff. So you have to have two different groups on your carbon where the double bond is to allow for this as well. Now, where does the cis and the trans come from? The cis refers to the two larger groups connected to the carbon-carbon double bonds are on the same side. Cis means same. And then the trans means the two larger groups that are on the double bonds are on opposite side, like one's below, one's above. Trans means opposite. And basically, what you need to do is you need to be able to recognize which molecules are cis and trans versions of each other. In other words, diastereomers. If I told you to draw diastereomers, could you draw those diastereomers and could you name them? Naming them is pretty straightforward. You just have to recognize that if you have the cis version, put a cis in the front with the hyphen. If you have the trans version, put a trans in the front with the hyphen. So, how do you identify if molecules are diastereomers? First of all, check if they have the same molecular formula. Check if they have the same bonding sequence, meaning the same name, the same base name. Check to see if there's a double bond. If there is, then the likelihood is that you can have diastereomers. Check to see that if each carbon around on the double bond has different types of atoms or groups of atoms bonded to it. Okay, so check that as well. So let's take a look here. Name the molecules below using cis-trans notations. So let's do that first. Let's go ahead here. We have just name this molecule as you normally would. So 1, 2, 3, 4, 5, 6. And it's on carbon number, the double bond's on carbon number 3. 1, 2, 3, 4, 5, 6. So we have a hex 3 ene. And notice this is the larger group on this carbon, and this is the larger group on this carbon, whereas H is the smaller ones. So since they're on opposite sides, this is the trans version of it. Trans hex 3 ene. Here's similar idea, 1, 2, 3, 4, 5, 6, with the carbon also, with the double bond also being carbon number 3. So we once again have a hexene, a hex 3 ene, I should say. But notice the two larger groups are on the same side, both above the double bond. So here we have the cis version of that molecule, and they will not interconvert from one to another because you have a double bond that prevents rotation. Let's take a look here. So the bond line diagrams are nice because the way they're drawn shows you if they're cis or trans. So when you have this zigzag pattern kind of going with a double bond there, that's automatically a trans version. And when you have this little table sort of pattern here, where you look at upside down table or even a table like this, that's right side up, then you know it's cis because your larger groups are on the same side. The only tricky part with this is you don't see the H's. In reality, keep in mind there's an H here, and here you have an H and an H. So if you want to help yourself by drawing those in, that could help you naming these. So here we have 1, 2, 3, 4, 5, 6, 7 carbons. And the double bond is on carbon number 1, 2, 3. So here we have an hept 3 ene. And here we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. So again, a hept 3 ene. Here are two larger groups. So here's one below the double bond. Here's one above it, above the double bond, going upwards, right? Upwards. This one going low. Or you can think your H's are on opposite sides as well. That's another way to look at it. This is the trans version. Here, your larger groups are both above the double bond, and your H's are on the same side. So this is your cis version. Cis hep 3 ene. They all have the same molecular formula, same bonding sequence, same relative order, just at that double bond region. That's where you have a different spatial arrangement in space. And that's what makes these two here cis-trans versions of each other, and these two here also cis-trans versions of each other. Let's try this next one here. Explain why the molecule below will not have a diastereomer the way it is drawn. So first of all, notice that you do have double bond. So you could technically have different arrangements about the double bond. However, remember, one of the requirements is that on the carbon where you have a double bond, both of them, you need different groups. So on this, this is one group over here, and then down here there's an H. Here, though, the group is CH3, CH3. You have two of the same groups, 2 CH3, on the carbon with the double bond. And so, therefore, there's no cis trans allowed or possible because it doesn't matter how you flip this, it's always still CH3. It doesn't give you a different arrangement about the double bond because it's still CH3 regardless. So that's why that molecule could not have cis trans the way it's drawn. Maybe if you move the double bond somewhere else, you could have a molecule with cis trans versions, but right now this one here just has is just a regular molecule, no diastereomer possible. So in this video, we saw a brief overview of what cis-trans isomers are. They're a type of stereoisomer called diastereomer, or also geometric. They require a double bond. One more thing to mention before we finish off here is cis can sometimes be called D or Z. So instead of putting cis, I can put D or Z. Trans is called E. So instead of putting trans, I can put E. And that relates to when you have groups that aren't quite different in size. So there we need sort of different priorities. And so based on the different priorities that IUPAC came up with, we'd use D or Z or E. We're not really going to focus on that too much. Just understand that it's another way to name cis trans if we had different priority groups that were similar in size. In the next video, we're going to take a look at how to draw some diastereomers of molecules. It should say diastereomers, not diastereometers.